In this lecture, we're going to introduce crystal field theory and how that affects the properties of coordination compounds. Remembering back a while ago when we talked about bonding, we talked about Lewis bond theory, we talked about valence bond theory, we talked about molecular orbital theory. Um, and valence bond theory is going to state that bonding will take place when filled atomic orbitals on the ligands of our coordinate covalent compounds are going to overlap with the empty atomic orbital of that metal ion, and that overlap is going to create the bond. And that explains geometries very well for our coordinate covalent compounds. But it doesn't explain the colors that we see from these compounds or their magnetic properties. And so it's not a complete picture, even though it does describe well that formal bonding that's taking place. And so crystal field theory will give us a more complete picture. And so crystal field theory says that, yes, these bonds arise from the attraction between the electrons and the ligand to the charge of that metal cation, and there's an overlap of those hybridized orbitals for the orbitals on the ligand. And that explains that geometry beautifully. And then it goes a step further and it says, but what is happening is we're bringing these electron clouds close to this metal ion. It has these hybridized orbitals that are interacting with the orbitals of the ligand, but there are still unhybridized d orbitals that are part of that metal ion that has some electrons in it, or even if they're completely unoccupied, there's still the orbitals there. And so the idea is that, well, those unhybridized orbitals will be affected by those electrons coming closer to it. In fact, they'll be repelled because the electrons in those d orbitals are going to have a repulsive interaction with any other electrons that come near it. And those electrons that are coming in from the ligand, they're attracted to the charge on that metal cation, right? And then they're getting this orbital overlap that allows for that covalent nature of that coordinate covalent bond. But so as those ligands come in and the d electrons are repelled from them, what happens is the energy levels of those d electrons change. So the more repulsion between a d electron in an orbital in the d orbitals and the ligand electrons, the more repulsion that is experienced, so the more direct overlap or like directionality to their coming close together, then, and the more that distance closes, the higher in energy those d orbitals will be. And so that's going to create a difference within the d orbitals. They won't be degenerate. And remember, that word degenerate means that as we've been drawing these when we talked about electron configurations and orbital diagrams, that our d electrons, let's call these our 3d electrons, are just all the same energy level. And so crystal field theory says the second you add ligands into the picture, your energy levels are very much not the same anymore. They're not degenerate. And we find that the ligand itself has a really big influence on how much the energy changes as it approaches the metal ion. And we see that we have what we're going to call strong field splitting and weak field splitting that occurs that'll be dependent on the ligand itself. And we have kind of a series to remember. So our weak field ligands are here and our strong field ligands are there at the top of this bar. And kind of here's our in between. And so we have weak field ligands that as it approaches will affect the electronic structure of that atom differently than these strong field ligands. And so let's take a look at that in more detail. So let's first focus on that overlap. And we're going to look at octahedral complexes, but this as our focus, but it's going to apply to all of our different geometries that we looked at. And the approach to thinking about the effect is the same. So I have a grid here, a plane, and I'm putting my ligands on the XY plane. So I have 6 things coming in, forming an octahedral complex. I'm going to go ahead and highlight my ligands a different color here. So I've got these 6 coming in. And now I'm going to overlay the different d orbitals that exist that will not be hybridized, possibly, onto the metal ion and see how they interact with those ligands, where the overlaps really are. And so let's look at these ones right here. So I'm going to just continue to put where the ligands would be here in blue. And when we're looking at our dz squared and our dx squared minus y squared orbitals, we're going to see direct, not necessarily overlap, but we'll bring those ligand electron clouds very close to our d orbital in the same direction. So they won't be off center from one another. And so here's my ligand, and on my dx squared or my dz squared, in the axial position, it's lining up perfectly with the lobe of that d orbital, which is right along that same axis. And then the electron density in the ring around that, well, that's hitting all 4 of the ones in the equatorial plane. And so the dz squared orbital is lining up perfectly with these ligands. And the same with the dx squared minus y squared. It runs along the xy plane. And so it is pointing directly at these 4 ligands that come in on those x and y planes to the metal itself. And so these both are going to have really direct contact or overlap with the ligand electron clouds, and they're going to see the most repulsion from that because they're coming closer together, which is bringing us back to Coulomb's law, that our energy goes up as we bring those same charges closer and closer together. And that distance and the magnitude of charge determines the amount of that energy change. And so if they're opposite charges, it's an attraction. And so it's stabilizing and decreasing the energy. And if they're the same charges, they're repelling. And so it's an increase. And so we'll see that the dz squared and the dx squared minus y squared will be higher in energy than we would predict. And then looking at our other ones, we can see that our dxy, dyz, and dxz are all very similar in that they have the lobes of the d orbitals in between the 2 axes on any 2 of our planes. And so dxy goes in between the xy plane. And so we're not going to have direct overlap. The orbital comes right in between 2 of our ligands. And so it'll still experience a repelling effect from those electron clouds of those 2 ligands. However, it won't be direct and head on, and so there'll be less, or there'll be more distance in between that d orbital and the ligand electron cloud. And because there's greater distance by Coulomb's law, that means there is less of an increase in the energy to destabilize it from those repelling forces. And so the same will apply for the xz plane and the and the YZ plane. And so we'll see that relative to the Z squared and X squared minus Y squared orbitals, these 3 orbitals will actually be lower in energy relative to it because there will be less of that direct overlap, or we'll say a larger distance from our ligands. So let's look at the effect of this on those degenerate energy orbitals, or the way we've been thinking of them as degenerate. So here's those 5D electrons that we're used to seeing when we do our orbital diagrams. And we're saying that 2 of these are going to be higher in energy than the other 3. But for all 5 of them, they're all going to be getting closer to these electron clouds from the ligands that will create repulsive forces. So they're all increasing in energy. It's just that 2 of them, the z squared and the x squared minus y squared, are increasing more. And so we see this crystal field splitting energy. And the splitting is coming from the orbitals' energies being different, and there being a split between the d orbitals. So we have 2 that are higher in energy and 3 that are lower. And this is going to look the same for all octahedral complexes. It'll be different when you change your geometry because the ligands are going to be coming in at different angles relative to one another and relative to those orbitals in the dx squared or in the x, y, and z plane. And so this crystal field splitting energy right here, we give it the symbol of a delta, and for change. It's going to correspond to the energy between the 2 levels of d orbitals after they've been split by the ligand field. And the amount of energy that is in between these, that difference in energy between our d orbitals, is going to correspond to the ligand type. And our strong field complexes, our strong field ligands, are going to create a larger difference in energy between the two. So we'll have a larger delta. And our weak field complexes, they're going to do, there's going to be smaller splitting. So there'll be less of a difference in between our two energy levels that are possible for our d orbitals. And so what the size of this is going to depend a lot on the ligand. But I'd like to point out that it also has to do with the ion itself. And so the oxidation state and the type of metal ion it is will also influence that splitting energy as well. And so it's both that impact it. So we can't directly compare like iron to copper or something like that. So the impacts of having weak versus strong crystal field ligands is that energy difference between our higher and lower states, if it gets large enough, will actually change how electrons populate the different orbitals. And so going back to orbital diagrams and thinking about how we place electrons into orbitals, we always half fill them. And so, and then we start doubling up. So typically with an iron plus 2, where we have 6 d electrons, we would fill 5 as single electrons in the orbital before adding that second electron in the first orbital here. Now, if we have a complex that splits our field and our crystal field and then has a small split relatively with maybe a weak field ligand like water around that iron, and let's go find water here. It's kind of in the middle, so it's, you know, it's technically a weak field ligand. Our cutoff here is at the NH3, between the NH3 and the H2O. So it's more likely that our electrons will populate themselves in a similar fashion that they did with just the iron plus 2 with no ligands, and that will fill all of our d orbitals with 1 electron before coming in and doubling up just in 1 orbital, just like we did before. But if we have a strong enough field ligand, and let's say we're looking at cyanide, which is one of our very strong field ligands, that energy difference between our higher and lower energy d orbitals is going to be dramatically larger, such that it's going to be more favorable to actually completely fill the lower energy levels first before adding electrons into the upper d electrons. And so then our electrons are going to go first 1 in each on the bottom, then pair up before adding into this top piece right here. And so that means that we're actually going to have 6 paired electrons versus 4 unpaired electrons and only 2 paired electrons. And that's significantly different when we think about the magnetic properties of this metal. These unpaired electrons are going to have a paramagnetic feel to it, and so it'll behave differently around a magnet than something that has all paired electrons. So try this problem out in the next video. I'll go over the solution, and it's drawing an orbital diagram just for the d electrons for these 2 titanium complexes.